functions, in some sense, it's not that different than graphing other functions. So it may be to our advantage to just review how we graphed functions, say, in algebra class or some of the previous classes. Let's just do a little review here. Suppose that you were in a previous class and somebody asked you to graph. Let's see. Suppose you wanted to graph y is equal to x squared. This is a famous one. This is a parabola, and there's a famous way of graphing it. But what I want to get to is, suppose that it was brand new for you. It was brand new. How would you even begin to graph, or what in the world does it mean to graph? To graph means to plot the points that satisfy the equation. So one of the ways that is pretty reliable, that almost never fails, well, it should never fail, but assuming that you can carry it out, but it's not, it's not always practical to carry it out, but it is here. So if we put x here, y here, here's the one thing that you can always try. If you got nothing going on for you, try this: plot points. That means you make a little chart here and you pick various values for x. For example, if x is 0, you plug it into the equation. You plug it into this equation, whoops, and into this equation. And when you do that, you should get a corresponding y value. If x is 0, y would be equal to 0. And meanwhile, what you're doing over here is you're making an xy chart, or xy plane, and you're plotting these points. And so, for example, 0, 0, that would be the point right here, 0, 0. And that's the beginning of your graph. Let me see if I can make it straight for you. That's good enough. But of course, that's not enough. Usually, the more points you plot, the better your graph will be, the more accurate your graph will be. If x is 1, you plug it in here. 1 times 1 is 1. That gives you 1. So if x is 1, y is 1. That would be approximately here. I'm just making stuff up. 1, 2, 3, 4, 5, whatever. 1, 2, 3, 4, negative 1, 2, 3. I'm just estimating, okay? Alright, so there's the point 1, 1, and it's still not quite enough. If you were to graph it, maybe just connect them, you'd really have a graph that's not really very accurate. Try some other points. The more, the safer you'll be. If x is negative 1, you'd have to go negative 1 times negative 1, that's positive 1. So when x is negative 1, y is positive 1. When x is 2, y is 4. When x is negative 2, y is 4. So it goes like this: 1, 2, 3, 4. When x is 2, y is 4. When x is negative 2, y is 4. And now you're starting to get something that is somewhat more representative of the graph. This is famous. This is called a parabola. This is a graph of y equals x squared. And this is the famous method called plotting points. It just means plot a whole bunch of them, enough to where you feel comfortable that you understand the pattern, and then connect the dots as smoothly as possible. Clear? You remember doing that, right? You remember. Of course, some other famous graphs. For example, y is equal to x. You would sit there and plot points. Y is equal to x. X, y. You make a little coordinate, and there you go. If x is 0, y is 0. If x is negative 1, y is negative 1. If x is 1, it's 1. If x is 2, 2, negative 2, negative 2. Then you plot them: 0, 0, negative 1, negative 1, positive 1, 1, 2, 2, negative 2, 2. Eventually, you get enough to see exactly what the pattern is. It's just a straight line. And there you go. Super famous. Super famous graph, super famous technique, plotting points. And super famous principle. The principle is, when you want to graph an equation and you've got nothing else going on for you, you can always plot points. I'm going to say that 1,000 times. That 1,000 times. No, I'm just kidding. When you've got nothing going on for you, you can always plot points. Make a little chart and start plotting. Okay, and the more points you plot, the more accurate your graph will be. Some other famous ones, the circle. I'll just plot a couple. X squared plus y squared is equal to 1. Super famous. If you've got nothing else going for you, you can always plot points. What happens if x is 0? If x is 0, that means this part is gone. Y squared is equal to 1. That would mean that y equals plus or minus 1. Plus 1 or negative 1. So both of these points are on the graph. Whoa. Let's make a little axis here. Happy little axis, x, y. When x is 0, y is 1. That would be somewhere around there. When x is 0, y is negative 1. That would be somewhere around there. And then you could pick other values. What if y was 0? If y was 0, x would be equal to 1 or negative 1. Right? Whoa, are you focused? Stay focused now. Yeah, it's focused. Alright, so this is 1, or when x is 0, this would be negative 1. So that means when x is 1, y is 0. When x is negative 1, y is also 0. And then you could try other points, for example, 0.5. If x is 0.5, that would give you 0.5 squared. That would be 0.25. Subtract it from that. That would give you that y squared is equal to 0.75. I'll just put a little thinking bubble. Y squared is equal to 0.75. So y is equal to plus or minus the square root of 0.75. And you compute that and you get some approximate answer. It would be a little less than 1. And there you go. When x is 1/2, y is equal to the square root of 0.75 or negative the square root of 0.75. And so on and so forth. You realize something for fun. If you plug in, what is going on with this focusing thing? Why aren't you guys staying focused? Alright, is that better? You guys needed some focus medicine, huh? Alright, I think it's good now. And I wanted to try something for fun. What if x is equal to 2? If x is equal to 2, I'll put a little thinking bubble here. Think. If x is equal to 2, what's 2 squared? That would be 4. Subtract it from 1, that would be negative 3. So you get that y squared is equal to negative 3. So y would be plus or minus the square root of negative 3. That would be plus or minus I times the square root of 3. That's an imaginary number. Non-real number, as a matter of fact. This is real numbers, this is real numbers. This one is not a real number. This is plus or minus I times the square root of 3. It's actually not on this picture. This is a picture of real x's and real y's. The complex would be off of that page somewhere in different dimensions. So you should also be aware that when you're plotting these points and you're playing this game, sometimes you get something that's not real, so you wouldn't see it in the real picture. Okay? And often, when people graph these, the implication is, people hardly ever say it, but really what they mean is graph the real solutions to this equation. Yeah, sometimes they'll just say graph the equation. What they really mean is graph the real points in the real solutions to the equation, because in theory you could also graph this. You just need some crazy paper that would come off of the page and into some other dimension. Let's just let that slide for now. Okay, when the student is ready, the teacher will appear. All right. Anyways, so then you plot enough points and then you connect the dots, and this is famous. A circle with radius 1. Alright, that's enough review for you. This is back from algebra class, okay? Remember, let's keep focused. What's the point of today? Today what we want to do is graph the trig functions. This is a trig class, so enough of the review here. We reviewed a famous one, a parabola. We reviewed a famous one, a line. We reviewed a famous one, a circle. Okay? Let us see what would happen if we graph, for example, y is equal to sine x. There you go. That looks more appropriate for a class. So you'd have to make a chart here. You don't have to, but this is, again, when you've got nothing else going on for you, the one thing you can always try is plot points. That's the theme of today. you got x and y. So let's try various. My x values are going to be either angles in degrees or in radians. And then I'll make a little x-axis and a y-axis here, and we'll start plotting. Actually, let me move this one. I'll move it right there. Okay, and then we'll start plotting. No, actually, I think you can't see it now. Can you see it there? Yeah. Stay focused, my friends. Okay, so now, hold on. Okay, so here we go. We start plotting points here. In this case, they would be angles. So let's go with some of the famous angles. For example, 0, 30 degrees, 60 degrees, 90 degrees. Start off with those. If x is 0 degrees, and you put it in here for x, sine of 0, well, you'd have to imagine a 0 degree, that would be an almost triangle. The opposite would be 0, 1, 1. So this would be 0. For 30 degrees, you do the same thing here. For this would be, the opposite would be a half of the hypotenuse, so this would be a half. For 60 degrees, it'd be the square root of 3 over 2. For 90 degrees, it'd be 1. And lo and behold, you've got a few points already to plot. 0, 0. We got to break up the axis into degrees, so we'll go with, let's put the 360 degree mark here. That would mean that in between here, it would be the 90 degree mark. No. This is 360. In between would be the 180 degree mark. In between here would be the 90 degree. Here would be 270 degrees. Okay? By the way, you can also do this in radians. This would be 2 pi. In between would be pi. In between would be pi over 2. And in between would be 3 pi over 2. Okay? And also you can do the negative degrees. Way over here would be negative 90 degrees. Negative 180 degrees, etc., etc. Alright, so once you've got enough points here, we'll just start plotting them. 0, 0, that puts you right here. Let me do this in orange. 0, 0 is right here. 30 degrees, that would be 1/2. 30 would be 1/3 of the way from 0 to 90. You see, from here this is 0, this is 9 degrees. So 30 degrees would be 1/3 of the way. That would be right around here. The ratio is 1/2, or 0.5. This is 1. At 60 degrees, it's square root of 3 over 2, so I approximate about 0.7. At 90 is 1. At 180, you should plot these in the homework. I set up a graph or a little table where you plot a whole bunch of them. For the non-famous ones, you'd have to use a calculator and get an approximation on the right-hand side. For example, 100 degrees, you would plug in the calculator, sine of 100, and get the approximation. And eventually you would plot all these points, and I'll just save us some time here. The points would go something like this. The highest point, the highest that the ratio goes from adjacent to opposite is 1. The lowest is -1, and it happens at 270. And so your graph would look very famously like so. That right there, that's a super famous graph. It's a graph of the sine function. And that's just for the angles between 0 and 360. You can actually put in there other angles, like negative angles and angles beyond 360. And what would happen would be that this graph here would get, this portion of the graph would simply get repeated a bunch of times. So, yeah, I mean, now just try to imagine what would happen if we plot points beyond 360. For example, suppose we plotted 390. At 390, you would go all the way around 360 and go again 30. This would be your reference triangle for 390. And it would end up with being exactly the same ratio as the one for 30 degrees, so you get exactly the same y value, 1/2. So you'd start repeating, every one of these values would start getting repeated again. And so the fancy way to say that is that this is a periodic function, meaning that the values of it get repeated for different portions of the x-axis. This portion, for example, would get repeated, and it would look exactly the same as that one, but of course it would be moved over here, and from 360 all the way to I know you can't see it, but from 360 all the way to 720 it would get repeated exactly as it appears here, and it would get repeated on the other side too. If you were to paste it, I mean, think about it. If you were to do negative 30 degrees or negative 330 degrees, you'd end up exactly the same spot there. It would be 1/2. So from negative 360 on to the right, it would get repeated exactly the same as it did in this piece. So the famous way to describe that is to say that that's a periodic function, and the number that's assigned to that is called the period, which tells you exactly what length is required on the x-axis for the values to start repeating themselves. So the fancy way we say that is, we say that this function is periodic with period 360, and I'll make a little box to show you exactly one period. That right there, that's called one period. Okay, we say that the period is 360 degrees, or 2 pi. But by the way, these also have another famous feature called the amplitude. This right here is called the amplitude. Amplitude is 1 in this case. It's the height on this very symmetric graph. Okay, that's a sine graph for you. Super famous. When you got nothing going on for you, you can always plot points. It's incredibly important that you plot points at least once or twice in your life. That's why I've set out these problems on the homework, where this exercise is really important, and you really do get more out of it by actually doing it yourself than by just watching me do it. So I hope that you'll get a chance to look at those exercises and actually carry them out, so you can get to know the graphs. Okay, let me make another version of this graph and point out some really important things about it. Most of the time you should know that it's quite common to only graph one period, and it's understood, even if I just graph that part of it, it is understood that for sine, or for all these actually, sine, cosine, tangent, for all of these, it is understood that even if just one period is graphed, they really go on forever, and forever that way and forever that way. Just as, well, a little different, but in a similar way, when we graph this parabola, it's understood that it goes on forever. Back here I put these arrows just to be consistent. I really should have put the arrows here to indicate that these go on for a long time. Okay, but sometimes I forget to put the arrows here. And in fact, it's more common that people just draw a period like that. Anyways, let me say a couple more things about that graph. So from now on, forever, it should be automatically clear that whenever you see a graph that's roughly like this, stops at 360. Sorry, 360. The middle is 180. The height is 1. The lowest point is -1. Automatic. Every time you see this, it's for sure it's sine x. Y is equal to sine x. Now you should become so familiar with this graph that you immediately know important features about the sine function. From now on, you can just look at this graph and say, hey, this point right here tells me something famous. Sine of 0 is 0. This point right here tells me something famous. The midpoint between 0 and 180 is 90 degrees. So the sine of 90 degrees, just by looking at this spot right here, you know something really famous about the sine graph, or sine function. What's sine of 90? Sine of 90 is 1. So see, now we're going backwards. Instead of using the values to plot the graph, we're going to use the graph to find the values. Sometimes you can do that once you're very familiar with the graph. Here, this tells you something famous. What is the sine of 180? Immediately, quicker. Sine of 180 is 0. 270. What is sine of 270? Quicker. It's -1. What is sine of 360? Immediately. 0. What is sine of 100 degrees? Quickly, a little less than 1. See that? That's got to be automatic once you get to know the sine graph. Okay? And in the same way, you should get to know the graphs for all the other functions. Like I said, that exercise is so important that you actually sit there and plot points at least a few times in your life. I can't stress how important that is. I'll talk about these graphs a little bit just so that you get to know them famously. The cosine graph, I will let you plot points at home. I'll tell you summary here. It goes like this. It starts off at 1 and it dips all the way to -1. It also has period 360. It is also periodic. These pieces get repeated, but you see it's slightly different than the sine. This one right here is y is equal to cosine x. Super famous. Again, after you've plotted points and you know the graph, now you can use the graph to find famous values. For example, this right here, this point tells you something famous about the sine graph. What does that tell you right there? It tells you that the cosine of 0 is 1, automatic. The midpoint between 0 and 360, that would be 180. Immediately, just by looking at 180, you should know what the cosine value is. So long as you become so familiar with the graph, and now you can even use the graph for the points. What's cosine of 180? Quickly. Well, -1. This tells you something famous. Between 180, and sometimes I forget to put the degrees here. Between 180 and 360, you find 270. What's cosine of 270? 0. What's cosine of 360? 1. What's cosine of 90? 0. See, famous points on the cosine graph. Super famous graph. Graph of the cosine function. Period. Again, the period is 360 degrees. The amplitude is equal to 1. By the way, have you guys ever heard of FM and AM? Do you know who put the FM in FM radio? It's frequency modulated. So by changing the frequency, the period, you can change certain waves that will deliver different channels on the radio. And AM, who put the AM and AM radio? It's amplitude modulated. So by changing the amplitude, you get different kinds of waves. So there's some relationship between FM radio and AM radio that has to do with the type of waves that are emitted and received by the receiver. Okay, I'm getting out of my comfort zone, so I'll stop there on that topic. Anyways, so some of the super famous graphs. This has to be so famous that you're gonna know it automatically. As soon as somebody shows you this graph, automatically sine. As soon as somebody shows you this graph, automatically cosine. It's gotta be just like breathing, just like walking. You don't even have to think about it. Cosine graph, it goes just like that. Starts off at 1. You see the difference? This one starts off at 1, goes down, dips in the middle, and goes back up. The other one starts off at 0, starts climbing at 90 degrees. It reaches the maximum, which is 1. By the way, from far away, they both look the same. Let's do a far away picture, just for fun. I've never done a far away picture. Let's do a far away picture. See if you guys can guess which is which. I don't think you guys could. I'm just kidding. I'm sure you could. From far away. Super far away. This is what they look like, and you might think, well, they look the same. Well, yeah, at first glance they look the same, but they're different. This one right here is y is equal to sine x, because it starts at 0, 0, and climbs up. This one is y is equal to cosine x. It starts at 0, goes down, back up. Okay, so these are many periods of this function. These are few periods of this function. This is what they look like from far away. Okay, those are the most famous ones, sines and cosines. Now let's get to the other kind of famous ones. Okay, those are the most famous ones, sines and cosine. The rest of them, they all have asymptotes, because they all have the possibility of having a 0 in the denominator. So we had this idea before that every single angle has a sine and a cosine value. but not every angle has a tangent value or secant or cosecant. That's because these other functions may have zeros on the bottom, so we have to exclude some of the angles from the domain. The best place to see that is on the actual graphs. For example, let's do a tangent. Y is equal to tangent x. Again, if you're a total beginner, you always got one thing going for you. You can always try to plot points. And I hope that you got the chance to, or you get a chance to do this on the homework. Plot some points, plot some points. This plotting point stuff is kind of boring for me, so I'm not going to do it. I'll trust that you did it. But when you plot points, you'll get something like this. Tangent of 0, 0. Tangent of 45 is 1. Tangent of 90 is undefined, actually. And so you have to refine your graph. Maybe try tangent of 10 degrees, tangent of 20, etc., etc., etc. Eventually, you'll get a picture that looks more or less like this. And there is a famous asymptote here, which means it gets really, really close to it, but doesn't quite touch it in the real plane. This asymptote occurs at 90 degrees and negative 90 degrees. And here's something interesting for you. The tangent graph actually has a different period. The period is from here to here, 180 degrees. 90 here plus 90 here, a total of 180 degrees. And this piece right here gets repeated over and over again. Whoa. Just kidding. Here would be the other asymptote, and you'd have another copy of the sine graph right around here. If this is 90 degrees, that's 90 degrees plus 180, this would be 270 degrees. And of course, I didn't draw it the same. I really did mean to draw it exactly the same as that. It should be 270 degrees, just like that. And there are many copies of that with many asymptotes. From this picture, it's clear to see. Just practicing. It's clear to see what the this is 0 degrees. This is negative 90 degrees. It's clear to see which angles have to be omitted from the domain for the tangent function. Can't have any tangent of 90 degrees, it wouldn't be real. Tangent of 270 degrees is not a real number, etc., etc. The other thing to notice is that these guys the ratio could be as high as possible. It could go all the way to infinity. Super famous graph, tangent. You should get to know it. The other thing too is, of course, make sure that you plot points. At least once in your life, you should plot points, say from negative 90 to positive 90. You might want to try intervals of 10 degrees. But don't try 90 because your calculator probably can't handle that. Try negative 80, negative 70, all the way to positive 80. And you plot the points. Super famous graph, tangent of x. The period is 180. It's also periodic. Some of the other ones. Let's do, for example, y is equal to secant x. Again, if you're a total beginner and you've never seen this graph before, the one thing you can always try is plot points. X, y. And what you may want to try too is try since the secant is the inverted cosine, you might want to try something like this. For example, 60 degrees. The cosine of 60 degrees is 1/2. The secant would be the inversion of that, so you would invert it. This would be 2. And that's how you could plot points, because most calculators don't have a secant value. For example, the cosine of 0 degrees. Cosine of 0 degrees is 1. You invert that, you flip it, you still get 1. And so eventually you will plot points and you get a graph. You could plot points there and just simply connect them. But let me give you a different idea too. Sometimes it's nice to see other ideas. Another way to look at it is to first draw the cosine graph. You know, the cosine graph is famous. It looks more or less like this. I'll draw 2 periods this time just for fun. Okay, that's the cosine graph. Y is equal to cosine x. Now you realize that the secant is the inverted cosine. where you multiply it, you take the reciprocal. So every one of these numbers has to be inverted. So, for example, well, this number is 1. 1 over 1 would be 1. This 60 degrees is, this one was, for 60 degrees it was 1/2. If you invert it, you get 2, so this would go up here. If you take these ones and you invert it, they would go up here. It's almost as if you were taking every one of these and inverting them that way. And of course, a 0 inverted would be very, very big, at least starting from this side. So you get an asymptote there. Everywhere that you have zeros, when you invert them, you're going to have asymptotes for the cosine graph. So these were all asymptotes. Okay? The other ones, what you're doing is just inverting them. So here, I'll just invert. That's what it would look like. You really shouldn't touch it. It really shouldn't. It just gets really, really close to it. But doesn't touch it in the real plane. Well, that's... Hopefully you get the idea. That's it. And of course, these go on forever. And so this is super, super famous. Y is equal to secant x, the inverted cosine. So I mean, roughly speaking, again, if you've got nothing else going on for you, you should plot points. Here's another way to look at it. Just draw the cosine, and whatever, if it looked like this, you invert it, and now it looks like this. And you just remember, all the zeros become asymptotes on the secant graph. If you accept that, then it becomes easy to do the other ones. For example, cosecant. Let's do cosecant. Are you guys afraid? Let's clear this page. Let's do little cosecant. So I'll draw the graph here. I'll draw a straight graph. And then what I want to draw is, I want to draw y is equal to cosecant x. And the first thing I think, there you go. First thing I think about is, what is a cosecant? Well, a cosecant is an inverted sine graph. So what I'm going to do is I'm going to draw the sine graph. The sine graph I know is famous. It looks like this. I'll draw a few periods. That should be enough. This is y is equal to sine x. Capiche? And then I'll think about inverting it. Inverting it would cause all these zeros to become asymptotes. Asymptotes, asymptotes, asymptotes. Every time you have a 0 here, you invert it, you're going to get a non-real number. And that's going to be my guiding principles. By the way, well, never mind. I'm going to use those as a guide so I can invert the sine graph, and it would look like this. Invert it, invert it, invert it. I can't believe I get paid to do this. So easy. And there you go. That would be the cosecant graph, just like that. Okay? Easy? Alright, so let me think. Let's review here. Sine graph. Oh, you gotta know the sine graph. You cannot go through life if you don't know the sine graph. Super famous. Cosine graph. Super, super famous. Tangent graph. Not so famous. Still worthy of mentioning. Secant. Got it. Cosecant. Got it. I think there's one more missing. What is missing? Of course, the cotangent. So let's do the cotangent. Okay, so for the cotangent, I drew the tangent graph here. This one is y is equal to tangent of x. And what you've got to do is invert this one. The cotangent is a inverted tangent. So here's what happens on these. Every one of these zeros becomes now an asymptote. That will become an asymptote for the cotangent. This one will become an asymptote for the cotangent. And the asymptotes for the tangent become zeros. So in other words, you got to flip this. So this points this way now. If you flip it, it'll now go this way. Let's actually do it. So this will go this way. This will be the asymptote now. This will be the 0 now. And then it'll look like this. This will go the asymptote. This will be the 0 now. That was terrible. It will look like this. Okay? So the asymptotes become zeros, and the zeros become asymptotes. That might be the best way to remember. And again, if you're a beginner and you've never done this before, I can only say one thing is so important for this entire lesson. When you've got nothing else going on for you, you got to do this game. You got to play this game. X's and Y values and connect the dots as smoothly as possible. Plot points. But hopefully you do this enough to where it becomes natural. A couple things should be really important. The sine graph, there's no excuse for not knowing the sine graph. You need to do this maybe 1,000 times, as long as it takes for you to become incredibly familiar with this sine graph. Okay, cosine graph, unexcusable. You must know this. Okay, if you don't know this, you need to sit down and learn this. It's so important. The other ones, they're okay. They're famous. I can live without knowing them all the time. You can always, as long as you know how to get them back, you know that you can always create them by just plotting points, or using some of the ideas that we used where we using this inversion idea where zeros become asymptotes, asymptotes become zeros. If you understand that concept, which is really important, you can always derive all the other ones from the two basic ones, which